Welcome to Rosmaya Muhtar YouTube channel.
Hi everyone, I am Madam Rosmaya. Welcome to my YouTube channel. So in this video, we are going to discuss on kinetic theory of gases. So we are going to solve one problem on this topic. So this is the question. So we read the question first. When an ideal gas is taken from the state X to Z along XYZ, the heat supplied for the stage XY and YZ are 182 joule and 65 joule respectively. So here X to Y 182 joule and Y to Z 65 joule. So the temperature of the gas at X, Y and Z are respectively 300 Kelvin, 400 Kelvin and 450 Kelvin. So here is 300 Kelvin, here is 400 Kelvin and at Z is 450 Kelvin. So question A, what is the increase in internal energy of the gas during the process XYZ, and explain why the increase in internal energy is different from the value of the total heat supplied. So we do question A first. So this is the formula that you need to memorize for this chapter. So we are going to use the first law of thermodynamics. The heat supplied equals to the internal energy plus the work done. Okay. So the increase in internal energy of the gas during the process XYZ. Okay, so we do Y to Z first. Okay, using the first law of thermodynamics. Heat supplied equals to change in internal energy plus the work done. So Y to Z, here there is no changes in volume, because this is the graph P against V, so this is a vertical line. So this means no changes in volume. So that means there is no work done. So the work done equals to 0. Okay, work equals to 0. So Q is equals to change in internal energy, delta U. So we can substitute QYZ here into here. So we get the internal energy is equals to 65 joule because it's equals to the Q. Okay, so this is for YZ. Okay, next we do for XY. So for XY, there is a changes in volume. Okay, X to Y. So therefore, there is a value for the work done. But unfortunately, we don't know this value. The work done, we don't know. So the Q given QXY is 182 joule. Okay, but because we don't know work done, so we cannot use this first law of thermodynamics equation. So we can use the another formula for the internal energy, which is equals to N CV delta T. So CV is the molar heat capacity with at constant volume. Okay, N is number of moles and delta T is the change in temperature. Okay, so we substitute the change in temperature. So 300, 400, final 400, Y 400, X is 300. So the change in temperature is 400 minus 300. So the problem is the CV. Okay, molar heat capacity at constant volume. Okay, so to calculate the molar heat capacity at constant volume, okay, we can calculate from here, where the internal energy equals to NCV delta T for this part. Okay, so we can equate it to 65. Okay, 65. Okay, then we can get the CV and we can substitute into here. Okay, so this is for the same gas. That's why the CV is the same. Okay, for XY, X to Y and Y to Z. So they comes from the same gas. So CV is the constant. So we can calculate from X, Y, Z to get the CV. Okay, so we substitute the temperature for Y to Z is 450 minus 400. Okay, so we rearrange the equations, become CV equals to 65 per n times 50. So we can substitute into here. Okay, so we can cancel out the n. So the internal energy is 130 joule. Okay, so this is internal energy x to y, for x to y. For y to z, we get 65. So therefore, the total of internal energy will be 130 plus 65. So we get 195 joule. So this is the first question. Increase in internal energy is 195 joule. Okay, next we are going to explain why the increase in internal energy is different from the value of the total heat supplied. So what is the total heat supplied? Total heat supplied here 182 plus 65. So the total heat is 247. So compare these two values. So they are different, right? So total of energy is larger in value compared to the internal energy. So why this happen? Okay, this happen because of the work done. From Y to Z, there is no work done. Okay, but for the X to Y, there is a work done. Okay, because of the changes in volume. So this part, 182, 130. So this value 130 become less because of the work done in the changes happened from X to Y. Okay, so question A is done. So next we go to question B. Okay, for question B, we need to use this. So we remain it here. Okay, the calculation we made it here. So we read question B. So determine the value of gamma. So what is gamma? Gamma is the ratio of the principal heat capacities of the gas. Okay, then state whether the molecule of the gas is monoatomic, diatomic, or polyatomic. So gamma is the ratio of the principal heat capacity of the gas. So the formula is given by ratio, right? Ratio. So molar heat capacities at constant pressure divided by molar heat capacities at constant volume. Okay, from this equation, CV done already from the previous question A. So next is what we need is to calculate CP. Okay, molar heat capacity at constant pressure. So we use Q equals to NCP delta T. Okay, so the Q, okay, constant pressure is X to Y. Okay, here is constant pressure. Refer to the y-axis here, P. So it's horizontal line. So this is constant pressure. So the Q is 182 joule. So we substitute the 182 joule here. Okay, the temperature change X to Y is 400 minus 300. Okay, so we substitute into here also. So we calculate CP. So we rearrange the equation. We get CP equals to 182 per n times 100. Okay. So now we substitute CP and CV into the equation of gamma, ratio of the principal heat capacities of the gas. Okay, we can cancel out n and solve this. We get 1.4. So for 1.4, it means that the atom here involved is the diatomic. Okay, the gas is the diatomic. Okay, so you must memorize this for 1.4. Okay, the formula for gamma in terms of degree of freedom is F plus 2 per F. So for diatomic, the degree of freedom is 5. So 5 plus 2 per 3, we get 1.4. So using another equation for gamma, Cp per Cv, you get 1 per 4. So that means this is a diatomic gas. Okay. So the changes of gas, this gas X to Y to Z is the diatomic gas. Okay, so done for question B. So next we calculate C. So for C, we are going to calculate the number of moles for the gas. Okay, number of moles for the gas. So that's mean N. We are going to calculate N. So refer to the equation here. So we need to use the relationship between molar heat capacity at constant pressure or constant volume with the degree of freedom, F. So we are going to use this equation. Okay. Okay, the equation here, I rewrite the equation here. So CPM is half bracket F plus 2 times R, and CVM is half FR. Okay, so F is 5 because just now we get diatomic, for that atomic the degree of freedom is 5. Okay. So using the CV equals to half FR, so F is 5. Okay, so R is 8.31. Okay, molar gas constant. And then we substitute CV, this CV into here. Okay, so we can calculate the N value. Okay, we are going to use this. So the N we get 0.0626 mole. Okay, we can also use this CP equals to 182 per N times 100. Okay, so this time we substitute half bracket F plus 2 times R. Okay, so F is 5, so half 5 plus 2 times R, and R is 8.31. So this CP we substitute into here, and we still get the same values, same value, which is N equals to 0.626 moles. Okay, so this is the answer. Okay.